We're looking at the second part of complex coordinates. So we want to find the product of the complex numbers z1 and z2 where they're both in polar form. And like we just said, the lovely thing about polar form is that you just multiply the moduli, the two r values, and you add the arguments, the two angles. So we've got z1 is 2, and remember CIS is cosine plus I sine, and the angle that's filled in goes for both. So I'm going to use this notation. We've got 2 cis 2 pi over 3 and z2 is -3 cis pi over 4. And to find the product, we're going to take the product of the r's and the sum of the angles. And R1 and R2 are 2 and -3. Now we need to add the angles. Three and 4 are what we call relatively prime numbers. Which means that even though 4 isn't a prime number, it shares no factors except 1 with 3. And that means that when we have numbers like that in denominators, we have to multiply 3 by the 4 and 4 by the 3 to get a common denominator. So we get 8 over 12 and 3 pi over 12. And so that sum is 11 pi over 12. The product of the r's is -6. So we would say that z1, z2 is -6 cis 11 pi over 12. Well, what about finding quotients? What about dividing these things? When complex numbers are in rectangular form, that means that in the denominator, I've got c plus di. I have an I in the denominator, which I don't want. I want I want z1 divided by z2 to be in the form, I'm going to use a and b again, a plus bi. In other words, I want one number that is the real part and another number that's multiplied by I, no i's in the denominator. So what we're going to do is multiply by the conjugate of the denominator. So let's see. Let's do example 9. So we're going to let Z1 be 3 minus 4i, and Z2 be negative 2 minus 2 square root of 21. And we want to find Z1 divided by Z2. Well, if we just write it in, let's see, we've got 3 minus 4i divided by negative 2 minus 2 square root of 2i. And the conjugate for the denominator is negative 2 plus 2 square root of 2i. We just changed the sign in the middle. And I want to multiply numerator and denominator by that. Negative 2 plus 2 square root of 2i, negative 2 plus 2 square root of 2i. Well, we know the product of conjugates. We know that a plus b times a minus b is a squared minus b squared. So here in the denominator, we're going to have negative 2 squared minus 2 square root of 2i squared. So that second part we're going to square carefully. So negative 2 times negative 2 is 4. Now we have 2 squared, that's 4. Square root of 2 squared is 2. And I squared. I squared, well, that's the way that we defined I in the first place. I squared is negative 1. So I've got 4 minus 8, because 2 times 4, times negative 1 for the I squared. That's 4 plus 8, and that's 12. So the denominator is going to be 12. So right now we've got 3 minus 4i times negative 2 plus 2 square root of 2i, all divided by 12. So all we have to do is distribute the numerator, find the product of the numerator. We can do that. So we've got, there we go, 3 times negative 2, 3 times 2 square root of 2i, that'll be 6 square root of 2i. Negative 4i times negative 2 is positive 8i. Negative 4i times 2 square root of 2i. So, gee, that's a lot. Negative 4i, 2 square root of 2i. Well, that's 8 square root of 2 I squared. And I remember that I squared is negative 1. So now this whole thing becomes positive 8 square root of 2. So let's see. We have negative 6. I'm going to move this positive 8 square root of 2 to the front. instead of the last because it's a real number. And then we have plus 6 square root of 2. Was that positive? Yeah. Okay, so plus 6 square root of 2i plus 8i. But I still have two I terms. So I want to write this as negative 6 plus 8 square root of 2 plus 6 square root of 2 plus 8i. That's the numerator. And now our quotient, z1 divided by z2, is negative 6 plus 8 square root of 2 divided by 12 plus 6 square root of 2 plus 8 divided by 12i. And it looks like we can divide through by 2 everywhere because every single number is even. So negative 6 divided by 2 is negative 3. 8 divided by 2 is 4. Square root of 2 is part of that same term, so we don't change it. 12 divided by 2 is 6. 6 divided by 2 is 3. The square root of 2 is attached. It's the same term, so we don't mess with that. 8 divided by 2 is 4. And again, 12 divided by 2 is 6. So the quotient of those two rectangular complex numbers is this mess. That's fine. Let's divide two numbers that are given in polar form. Because in polar form, if you have the number z1, r1, cis theta 1, and z2 is r2, cis theta 2, to divide, you subtract the modules and divide the r's. And that's it. Really nice. Well, so let's do the example. So we want to find the quotient of z1 is 2 cis 2 pi over 3. Z2 is negative 3 cis 3 pi over 4. And Z1 divided by Z2 will be 2 divided by negative 3. So R1 over R2. And then the cosine plus I sine. And both angles are always the same, which is why this notation exists. So then we've got 2 pi over 3 minus 3 pi over 4. We have the same two denominators that we just had. And again, 3 and 4 are relatively prime because they share no factors besides 1. And that means to get a common denominator, when you have relatively prime numbers, you multiply one denominator by the other. So I've got 2 pi over 3 times 4 over 4 minus 3 pi over 4 times 3 over 3 That's 8 pi over 12 minus 9 pi over 12, and that's negative pi over 12. And we can't do anything to this modulus, the number out front. So we just have negative 2/3 cis negative pi over 12. And if you write it out, you can deal with this negative. So we have cosine of negative pi over 12 plus I sine negative pi over 12. I know that cosine is even. That means when it has a negative number plugged in, that it just goes away. So I've got negative 2/3 cosine of pi over 12. Sine is odd. That means when there's a negative inside, it comes out. So minus I sine pi over 12. This step is extra. This answer is fine. All right. Well, next time we're going to be looking at Demoivre's theorems. Oh, beautiful, beautiful stuff. All right. Have a great day. Bye.